Hi, welcome back. This is the fourth lecture of your Analytical Mechanics numerical practice class. Until now, we have solved the selective problems from chapter 2 and from chapter 3. Unfortunately, because of the shortage of time, it is not possible to solve each and every problem. So after reviewing the content of each chapter, I select the important problems and then solve those problems in the video lectures. But as I usually say, if you feel any difficulty while solving the remaining problems, you have the option to discuss with me. I think this is the best way to save our time and to cover the whole content of the course within the specified period. In this lecture, I will solve problem 4.7 from chapter 4. Chapter 4 is about the general motion of a particle in three dimensions. The statement of the problem is particles of mud are thrown from the rim of the rolling wheel. If the forward speed of the wheel is v naught and the radius of the wheel is b, show that the greatest height above the ground that the mud can go is b plus v naught square over 2g plus gb square over 2v naught square. At what point on the rolling wheel does the mud leave? Note, it is necessary to assume that v naught square is equal to and greater than bg. You will see the statement of the problem on screen now. Let R be a vector from the center of the wheel. To a location where mud particle leaves the wheel. Let R be a vector from the center of a wheel to a location where the mud particle leaves the wheel. As the radius of the wheel is b, so here I will draw a figure. Suppose this is the wheel, it has radius b So this is along x-axis and this is along y-axis. And this is its radius b, and this is the r vector in this direction. It has angle theta with the x-axis. So the x component here, the x component is b cos of theta, and the y component is b sine of theta. So from the figure we can write x naught is equal to b cos of theta, this one, and y naught is equal to b sine of theta. So for x direction, ax is 0, and v of x naught, it is equal to minus v naught sine of theta. This is equation 1. Similarly for y direction, ay, it is minus g because of the gravity, and v y naught is minus v naught cos of theta. So this is equation 2. So for position x as a function of t, we can write the equation for position x as a function of t. The equation is x as a function of t is equal to x naught plus vx naught t plus 1 over 2 ax t square. So here we know that the ax is 0, so this term is 0. So in this case, x we know that x naught is equal to b cos of theta. We have this value, and similarly we have the value for vx naught. So this is the vx naught. So we will put the value of x naught and vx naught into this equation. So finally we will get x of t is equal to b cos of theta minus this value v naught sine of theta. So this is the position x as a function of t. So let this equation is 3. So now the position y as a function of t is y function of t is equal to y naught plus v y naught t plus half ay t square. So now we have the values and we will put the value of y naught. This is the value of y naught, and then we will put the value of vy naught and then ay. So the value of vy naught is minus v naught cos of theta, and the value of ay is minus g here. So we will put these values. The final position of y is the position of y as a function of t. It is b sine of theta plus sorry, this is plus not minus, plus v naught cos of theta minus half gt square, and this is equation 4. Now these are the positions, like position of x and position of y. So we need the velocity equations here. So simply we can take the derivative of equation 3 and equation 4 with respect to time, and we will get the velocity. The velocity equations are taking time derivative of equation taking time derivative of equation 3 first, it is v of x minus v naught sine of theta, and because this term does not contain here, it should be t. So this term does not contain this term here, it should be time t. This term does not contain t, so this is 0. So only we have v of x is equal to minus v sine theta. So the derivative of equation 3 is v of x is equal to minus v naught sine theta. Now the time derivative of equation 4, it is y of x v of y is equal to yt. Basically this is the time derivative, and it should be equal to, the first term is 0, this term is 0 plus here is t plus v naught cos theta minus gt. So 0 plus v naught cos of theta minus gt. So this is the equation 5. At the maximum height of mud particle, the vertical velocity should be 0. That is, okay, let me write, at the maximum height of mud particle Vy is 0. Putting this value in equation 5, in this equation 5 becomes 0 is equal to V naught cos of theta minus gt. So here the T max is V naught cos of theta over g. From this equation, T max is equal to V naught cos of theta over g. Now we will put this value into equation 4. And this is the equation 4. So let's put the value of T max into equation 4. So equation 4 becomes Y max is equal to B sine theta plus V naught cos of theta. Here we will put the value of T max, V naught cos of theta over g minus half g t square. So here it is V naught cos of theta over g whole square. So here we will just simplify this equation. It will become Y max is equal to V sine of theta plus half V naught square cos of square theta over g here V naught square cos, yeah, so it is the simplified form. So we will say this is equation 6. We can further simplify this equation like Y max is equal to B sine of theta plus half V naught square over g into 1 minus sine square theta, because in the coming part I actually need an equation in this form, so I just simplified it. So now in order to maximize this with respect to angle theta, we will take the time derivative of we will take the derivative of equation 6 with respect to angle theta. So taking derivative of equation 6 with respect to angle theta, dy max over d theta b cos of theta minus V naught square cos of theta sine of theta over g. So to maximize this with respect to the theta, this term should be equal to 0. That is dy max over d theta should be 0. So putting this value in this equation, 0 is equal to b cos of theta minus v naught square cos of theta sine of theta over g. If we more simplify this, we can take common cos of theta, so it will be cos of theta into v minus v naught square sine of theta over g. So this is the simplified form. Here if we say that the cos of theta is equal to 0, if cos of theta is 0, then it corresponds to the minimum. Thus we will write like v is equal to v naught square over g sine of theta. Simply we put this form to 0. So from this equation, sine of theta is equal to bg over v naught square, or theta is equal to sine inverse bg over v naught square. So in order to prove the statement of the problem, which is y max is equal to b plus half v naught square over g plus half b square g over v naught square. So simply we will put the value of sine theta into equation 7. So this is the equation 7. So let's put the value of sine theta. Y max is equal to b into bg over v naught square, because sine theta is equal to bg over v naught, sine theta is equal to bg over v naught square, plus half v naught square over g into 1 minus bg over v naught square, then again square. So here we just need to simplify this equation. B square g over v naught square plus half v naught square over g because of this, and then minus half v naught square over g into this term b square g square over v naught 4. So here this g is cancelled, this v naught square is cancelled, so the remaining part is y max is equal to v naught, if we just simplify it, so it will become half v naught square over g this term, and then because these two terms are same, so we will just add them. So by adding them we will get 1 over 2 b square g over v naught square. I believe this is correct. So this relation, it is measured with respect to the center of wheel. So to measure with respect to the ground, we have to add the term b in this equation, an additional term here. So relatively to, okay, let me write. So you see that it is proved. So we can say that the theta this angle is the angle at which the mud particle leaves the wheel.